for electricity, right? Next is now we will talk more about today's presentation. At the end of this webinar, what do we expect to get? And at the end of this presentation, as I mentioned earlier on, this is a very huge topic. We'll try to cover a few items that are relevant to the topic. And from there, you can as well progress. Think about how you would progress the topic on your own. When we talk about the power grid starts from the power generation, transmission, distribution, all the way to the customer level. And in each of these category along the power grid chain, there are different technologies used and there are some similarities used as well. So for instance, if we talk about the power generations, let's take like a thermal power plant that is run on a natural gas. You would have transformers at the generation level. When you get to the transmission, you will have transformers as well. You will have circuit breakers. All these infrastructure or assets are the same, but they are used for different purposes. So if you look at the picture here, we have like a generation station where step-up transformers are used to step up the voltage to transmission level. It goes to a distribution substation where now we decide to the type of customers to produce electricity to. So it could be sub-transmission customers. For instance, if you are transmitting from a huge substation to, let's say, a mining or a huge an industry, you would as well need a sub-transmission voltage. And we have primary customer and then the secondary customer, which is like a domestic or household customers. And we would also look at today's grid. How does today's grid look? We have already seen like few examples how the grid started in the US in 1882 and in India 1897 and how they've all progressed. Some of the challenges for modernization. We will also discuss the critical parameters that we have to look out for grid enhancement. But all of this will not come free. They have potential benefit as well as difficulties and the risks that are also associated. We will also look at them briefly. So in today's power grid, how does it look like in India? India started 130 kilowatts, but today India has made a significant progress. There has been an exponential growth and they have been able to build an infrastructure that is capable of handling over 400 gigawatts. And this 400 gigawatt is not serving how India started, providing electricity just for offices, the palace, and then the tea estate. But now, this 400 gigawatt huge infrastructure is serving the fifth largest economy in the world. Fifth largest according to the world data. How about the United States? United States that started with 400 kilowatts, powering 59 customers within the first month, 500 within the first 1 year. It's now running over 9,200 generating units with over 1,000 gigawatts generating capacity. And all of this spread across 600,000 miles or 965,400 kilometers of transmission lines. I simply say this is, you can call it the giant grid. Um, and we will not be able to talk into details about everything about the US grid. US grid is very reliable, very stable, and I have been in this country for some time now, for over 6 years, and I hardly see a blackout or any power outage. So that tells you that the grid is very, very stable. It doesn't mean that there are no challenges, but to run a huge grid across 50 states in a very huge country without failures is something that is remarkable. Okay, now let's also talk about the factors that are leading to modernization. So from the beginning, we have looked at the word modern. To modernize means that to come up to date, to bring something up to date. And the world continues to evolve. So the world is evolving in technology, in how uh, even how we use our phones, everything continues to evolve. So the power grid as well has to evolve. But what is causing this evolution? What is causing this modernization? Why do we need it? Number one, there are several factors, but number one of them is energy transition. For instance, India aim at hitting 500 gigawatts of renewable capacity by 2030, 5 years ahead, according to an article by energyworld.com. You can simply say this is massive. To build a 500 gigawatt grid that is solely coming from renewable is huge. But traditionally, when power plants started, they started as hydro, thermal, conventional power generators. And now, to build something that is renewable energy that has high variability, as we all know, if you have a solar plant, the solar plant only operates when there is sunlight. In the night, it is total zero. You have zero production in the night. And so to transition from what is comfortable and to move from your comfort zone to something different is it means that you actually have to change the grade. The grade has to be up to date. So that's one of the leading factors. So moving from traditional sources to renewable sources is one of the reasons why we have to modernize our grid. And number two of them is increasing demand. As the population of the world continue to grow, and then also infrastructure continue to change. Previously, all vehicles, or even now, most vehicles run on internal combustion engine, which means that they either use diesel, petrol, or fossil fuel-based energy resources. So, if you run an internal combustion engine vehicle, your car is not relying on the grid to actually power itself. But now, changing to electrifying transportation, electric cars, trains, and then making buildings more smarter means that, and then also the master of all of them is the the fast adoption of AI that is also increasing the building of data centers. All of these are factors that are driving the demand. So once your demand is increasing, you need to generate more electricity to be able to meet the demand. And once you are generating more, then it means that you have to change the grid. So every grid, for instance, if you have a transmission line, the transmission line is built to carry a capacity. Every transmission line has a capacity. So if you build a power plant, let's say 100 megawatt power plant, and then you want to inject the 100 megawatt into the transmission network. You don't size the transmission lines based on 100 megawatts. Mostly transmission lines are oversized in expectation that there will be future expansion. So when there's future expansion, there's no need to change the transmission line because there's more capacity. But there's limits to everything. You cannot build something that is infinite great. But demand continue to change. So once the demand is changing, then what it means is that you would there would always be the need to change the transmission line or change some of the infrastructures. Okay. So increasing demand is one. In the USA, there's a huge, not as huge as other countries because US demand is increasing very steadily, like almost 2% for every year. So you can see some numbers here I got from the US Energy Information Administration. This is the most reliable source in the US. Uh, you can see the numbers nearly 2%. In 2024, there's 4,097 billion kilowatt hour of electricity usage. But in 2025, that increased to 4,189 kilowatt hour. billion kilowatt hour. And then it is expected that in 2026 there will also be an increase. If you look at the difference, it's about 2%. However, in India, according to other sources, different sources give different numbers, but I choose the highest one with a fast growth of 9%. So if there is an increase every year, you have 9% increase in demand. More people want electricity because of uh, heating and cooling, because of industrialization. Because India is a country that is fast growing. So a country that is fast growing means that there will be more need for electricity to power the grid, to power the economy. Uh, number Number three of them is aging infrastructure. Most of the power network that we have were built several years ago. And that was the first question in the quiz that we have, the true or false. Most power grids were built over 50 years ago. And in the US, 70% of US transmission lines are over 25 years. However, the life expectancy of these lines will be like 50 to 80 years, according to the US Department of Energy. And 25% of these lines are already over 50 years, which means that if you do the math, nearly 150,000 miles of transmission lines may require replacement. Okay, so when we look at this, we have US here, 50 states, India here, and this graph also shows the percentage of lines based on their age. Number four of them, of the reasons why there's the need to modernize is policy and regulations that support decarbonization. For instance, the Paris Agreement that was signed in 2015 is a policy for multinationals, like multi countries, that are all gearing towards decarbonization, reducing fossil based resources to renewable resources or more environmentally friendly energy production sources. So, this policy is a policy, however, it has an impact on how engineers will design their grid. And if you are an engineer, one thing you have to know is that most of the times we engineers love to think about only the engineering part of things, electrical, I want to do power, and then we forget the policy aspect. However, policy and laws are the most powerful instrument that determine how economies will grow. So, for instance, you can have one government today in your country that supports, let's say, uh, fossil fuel, and then another government will come and will not support fossil fuel, or a government will support renewable, and another government will not support. So this has huge impact on how the grid will actually function, or how engineers will proceed to design. Engineers alone cannot design. You cannot design and build a plant without having the business side of the work, or the policy side of the work, or the law aspect of the project. And this one, I have seen this a lot even in my current work, um, as working for a company that develop power plants across several countries. You would begin to understand that it's not only engineering, right? There are a lot of interdependencies: the law, the finance, the economic aspect of it, the marketing aspect of it, and even the huge part is also compliance. You have to build a plant that is compliant to regulations. The last point here I'll give is a cybersecurity and resilience. When we talk about cybersecurity, is the threats that power grids face. Now we are more in the modern world, everything has become more digital. So once you begin to digitize everything, it means that any system that is more digitized, is more connected, is online, can be hacked, or is people the bad people can actually hack the system and then try to change some parameters. So, for instance, if you are having a power plant and you don't have a strong firewall within your network, what will happen is that what will happen is that you would have uh, you would have threats, people hacking into this, and then could change the plant operating conditions. So once a plant operating condition is changed, then instead of the plant running smoothly, the hacker can actually trip a circuit breaker. And if you trip a circuit breaker of a huge network, what will happen is that there's huge loss of generation or a huge loss of load. This will cause an imbalance in the system. And once you have an imbalance between generation and demand, then you see frequency will change. And when frequency change, this will have a cascaded effect and can cause a huge blackout. So when we talk about cybersecurity, you need to think about it that way. Like, okay, cybersecurity is not only with IT systems; they are very interconnected. You can't run any power grid without security. And so once your security is not good, and then the bad people throw in some spams or try to hack your system, then they can actually affect the grid. Which therefore means that because of this threat, cyber threat, we need to modernize our grid with modern features of network security, strong firewalls, and most of legacy power plants or even uh, electrical systems do not have this. And you would appreciate and understand this more if you begin to work in the power sector, and then you look back and see that okay, 50 years ago most of the protection, even protection relays or metering systems that were installed were are very old, so they need to be replaced in order to be able to accept some of the modern or the latest technology in terms of security and network protocols. Okay, next, um, why all of this matters. We have already looked at 5 reasons why we need to modernize the grid. So the grid has to adapt to more to today's energy and technological needs, and also mitigate the threats and ensure the security of energy. In actual sense, a bad network or an old grid is a national security issue. National security in the sense that, for instance, if you have customers losing their electricity for the whole day, that would be very bad. Let's say people can correlate a power outage in 1 minute, 5 minutes. In most countries or developing countries, people will correlate it for one day. No, it's no problem. But in a very advanced country, people will not correlate that. There will be huge uprising, there will be demonstrations. So energy reliability is very related to national security. Lack of energy will mean that people can uprise, can take on the government and cause destabilization in any country. So that's why we need to modernize in order to be able to secure our native countries. And as the power grid continue to evolve from electricity generation from different sources, it also means that we need to adopt. Okay, let's look at some metrics that tells us that's re-emphasize what I'm talking about. For instance, if you look at the metrics in the US, the average outage in the year, the whole of the year is 7 hours per year. This is very different for many countries. So in the entire country, it is estimated that you would have a blackout of 7 hours, and this is different for different states. However, this is the average for all the entire country. And this outage, every outage comes with a cost. So power outage cost per year is almost $120 billion. In other countries, it may be different. We will look at an example where, um, for instance, in India, due to some technical losses, we'll look at that in the next 2 slides. So an outage is equal to losing money. If you have electricity production, this you can calculate the amount of energy that is produced in every hour, because energy is power times the time, right? So if you have 24 hours in a day and then you are producing, let's say, 100 megawatts for every 1 hour, that means that 24 times 100 megawatts will give you the amount of energy produced. So if you lose an hour or 7 hours, that means that 24 minus, let's say 24, you lose 4 hours. 24 minus 4 is 20 hours. That 4 hours that you have lost is lost in energy, which is also lost in revenue. So that's how we are losing. Uh, we are losing if our grade is not very good. Okay, now there's the opportunity that comes with modernization, and this has been estimated that in the US, with great modernization, there is the opportunity to uh, to have additional 80 megawatts. So this is, let's say, the base case. You have a grid that is old. The grid is old. It is 20 gigawatts in capacity, but based on using modernization, using advanced conductors that can operate at high temperatures and then at higher ampacity with less sag, you can increase the capacity of the same network from 20 to 100 gigawatts. And every single gigawatt in the US is estimated to produce electricity to 750,000 homes. So you could see 80 gigawatts multiplied by 750,000 homes. That will give you the total number of homes that modernization can lead to. So, in actual sense, modernization is good if we are able to bring our grid from how it was old to up to date. We'll be able to have the leverage to increase its capacity and as well as producing more power to people. Next, let's look at some reliability metrics in India. So in this webinar, as I mentioned, I'm mostly using USA and India, but it applies to almost every country. We have more than 100 countries in the world, so I'm only using only two. So the understanding is what we need to focus on. In India, you can see some metrics here of power losses, and we have technical losses as well as commercial losses. So technical losses will usually be something that is related more to the transmission lines. When there's power flow, definitely you will lose some of the power, right? Current flows, so current square times the resistance of the transmission line, that would be a power loss. In most cases, there would always be technical losses. There's no grid in the world that is 100% efficient, but we need to reduce these losses. And so, in the average transmission and distribution losses in India as of 2023 to 2024 was estimated 16.64%. If we approximate this to 17%, let's put this into perspective of generating 100 megawatts power from a plant. What it means is that if you have the power plant here and then the customer here, you produce 100 megawatts, but this 100 megawatt has to move from the generation plant all the way to the customer. Before it gets to the customer, you are losing already technical losses, technical losses for transmission and distribution, 17%. 17% for 100 megawatts means that you are losing 17 megawatts. What does 17 megawatt means? Every day is 24 hours. And then, for instance, let's say every megawatt hour, the cost of electric energy is $40. The cost of energy $40. When you do the math, revenue loss for every single month will be $489,600. If you calculate for the entire year, you are losing $6 million. $6 million. So, for instance, if this plant is to operate for 20 years, most power plants, we have power purchase agreement. In power purchase agreement, there will be the life of of the project or life of the plant. So either 20 years, 30 years. So multiply 30 years by $6 million. 30 years times $6 million. If my math is correct, that is like $180 million lost. This is huge. So you would understand why we need to modernize. If you modernize using advanced conductors instead of the traditional conductors that we use, we can use more the latest conductors that have been researched and been produced, and then also change the some things in the grid that will help us to reduce these losses. Apart from technical losses, we also have to remember that there are commercial losses. Commercial losses could be like people stealing the power and then doing bypassing of meters, energy meters. So you don't actually get revenue from producing the power. Okay, now we have built some foundation. We have looked at some history of how power grid started, looking at India and the USA, and then we have looked at the reasons why we need to modernize. We have looked at some metrics why, if we modernize the grid, some of the benefits, we will have increase in grid capacity, we'll be able to produce electricity to more homes and more customers, and then also we'll be able to, if you reduce losses, we'll be able to save the millions of dollars to our companies. But in order to modernize, we need to look at some critical parameters that engineers and all stakeholders have to care about. These are just a list or a few lists. This is not everything in the power grid that we have to look at. But for instance, if you are running a thermal power generation, you will need to look at the vibrations of your generators. Every generator that is running, you would have vibrations, right? So vibrations, even though they are more of mechanical, but there's a consequence of large vibrations damaging parts of the generator and then also the prime mover, right? So for instance, if you have frequency of the grid change, let's say you have a large customer and then there's an outage, the customer will have a trip at the customer end. Once there's a demand lost, then there's generation, more generation. So the frequency goes up. Once frequency goes up, the speed of the generators will be higher. And once you increase speed more than the nominal speed, what's happening is that the generators will begin to vibrate. And once there's vibration, you can cause mechanical breakage in parts of the generator and even the prime mover. So we need to monitor critical parameters. Number one, I have here vibrations. Number two, temperature is one of the most important parameter that we have to look at. Every project is not the same. If you build a project even in the US here, a project that will be built in Texas will not, the design parameters will not be the same as a similar project, let's say a 100 megawatt project built in Texas. The design parameters will be different from building that 100 megawatts if you are in Illinois, or maybe if you're in New York or New Jersey. It's the same thing if you are in Ghana. The design parameters of building plants in the southern part will not be the same as in the northern part. So the northern part is very hot as compared to the southern part. So this temperature difference plays a key role in design parameters, from how you size your cables and how even the inverters, for instance, if you're running a solar plant, how inverters will operate. There's a duration based on temperature conditions. So we need to know this critical parameter very well. Water usage. If every plant almost use water, but especially if you are running conventional power generations, thermal power plant, you will need a lot of water for cooling and then also for other plant processes. And also, when we run wind turbines, we need to know the speed of wind because this actually feed into how the power is produced. So we need to know data. We need to have some data of wind speed. If you have a solar plant, we need to have data of the amount of sunlight that is hitting the solar plant, the irradiance, and also our daily operational parameters will be the current, the voltage, the real power, apparent power, the power factor, and even the frequency. These are critical parameters that we need to look deep into. Next on the slide, also we need to also understand the dynamics of data and how disturbance or fault occur. And when there is a fault, always there is data behind the fault. As we all know, AI is more about data. You need to have a source. You need to have an input to be able to model an outcome or to be able to model an expectation. So we need to understand these critical parameters. We need to understand the grid operating conditions. And then also when there's a fault or a disturbance in the network, what happens? We need records. And then also we need to, another thing, parameter to look at is the emissions monitoring. If you run a coal power plant, you know obviously there will be a lot of emissions from CO2 gases and carbon monoxide and all the nitrogen oxides that will come here. We need to understand the data behind this. How was the plant built to operate? And then once we know that baseline, we'll be able to reduce the emission. But you need to have the base case. When we look at the transmission lines, you have this huge infrastructure here. You have insulators, you have the conductors, you have underground cables, and then how the transmission lines are sagging. So, we need data on all of this. And then based on that data, we will be able to say, okay, is the sag okay or is the sag too much? So once you have current flow and then there's temperature, these transmission lines will be heated. Once there's heat, there will always be some sag. And when the weather temperature changes or the ambient temperature changes and the place becomes very cold, there's possibility of contraction. So now you need to understand the contraction and the expansion of the lines and if they are within acceptable means. Okay, heat is also one of the things we need to consider as a parameter in operating our power grid assets, especially if you are running a thermal power plant. Heat is the main thing that goes to heat the water. You heat water, and then the water gets very hot. There's steam that will be produced from the water. This steam is dry, and then it runs through turbines to produce electricity. So you have heat, boil the water, you produce steam. The steam is dried and then goes through a steam turbine. And then that steam turbine is able, based on that speed and then the pressure, is able to turn a generator. So we need data on heat. And then also pressure. I already mentioned pressure, also a very important parameter. Not only in generations, but even in transformers, the pressure that is built up in the transformer, we need to have an idea of this. And weather resources, we need to know the weather very well. That will help us in forecasting, especially if you're running solar power plants or wind. Knowing the weather data is very important. If you are running a hydro power plant as well, you also need to know the weather because sometimes the water level goes down and then sometimes it comes up. Based on the head of the water behind the dam, we'll be able to produce electricity. So weather conditions are also very important parameters. If there will be sunshine in the next 1 week, we'll be able to tell. And then based on that, we can forecast the amount of solar energy or solar power that can be produced from solar assets, and so forth and so on. So we have looked at some few parameters. These parameters are important because they set the foundation, and based on that foundation, we'll be able to uh, plan for our AI optimization, right? Okay, now we have all of these parameters come with measurement. But once we have a measured data, what do we do with that measured data? But in the first place, if you are operating a power plant or the power grid, you have intelligent electronic devices that are installed in all the stations, like in substations and in other locations to monitor the grid, right? You have a protection relay. So intelligent electronic devices could be protection relays that have measuring capability to measure current, voltage, frequency on all the parameters. You have automation controllers, for instance, like real-time automation controller from XCL. All of this play a key role in measuring data and transmitting the data to a central point for monitoring. Right? So you monitor the data, gather all the data to a concentrator, right? Retrieve all the data. It goes into uh, a SCADA, right? Supervisory control and data acquisition. So it goes to SCADA, and then based on that, from that SCADA, we'll be able to have data for all the current and other stuff. Obviously, there are a lot of technologies here how to extract data from the grid. Smart meters, right? The smart meters are far better than previous meters, and this is a change. Old meters or even old protection relays do not have capability. Most of them do not have capability of measuring, uh, of producing phaser measurement, right? But in modern electronic devices, intelligent electronic devices, most relays and smart meters have the capability for phaser measurement. So phaser measurement means you have like current voltages. You need to measure these parameters within very short time. And so when there's a fault, you are able to diagnose and know that, okay, this fault, this is the records, the grid was working normal, and at this point it started to malfunction. And we have sensors, we have Internet of Things devices that can all record and send data. And why do we care about this data? Because this data is our input. Based on that input, we already have a factory acceptance test report or site acceptance test report, and then performance of the grid. Every grid has a performance history and report. Based on the measured data here, we can make a comparison. Let's say you are building your AI model to predict how the grid will function. Then, based on the history or the performance of the grid, and then when the fault actually happen, you'll be you'll be able to capture the voltages at each of the buses, the voltage and the angles, the phase angle at each bus, and then based on that knowledge, you'll be able to tell, okay, uh, if this type of fault is occurring, what happened before that fault? And so you'll be able to predict what will happen in the next event. If something like that is going to happen, immediately you see this clue, take an action, take a mitigation action. Either you are going to derate your generation or find frequency controllers to actually balance generation and then demand. And then once you're able to do that kind of balance based on the knowledge that you have, you would be able to prevent any outage or any cascading effect. So cascading effect will be a major fault that runs through the entire grid, and then collapsing a larger portion of the grid. So taking an action early on prevents a larger effect. Even if the effect will happen, it will only happen in a very smaller network and will not affect the entire grid. Okay, so since we know parameters to check, we know the importance of measuring the data and then setting our base case. Let's look at some of the applications that we can use this knowledge. So applications here, how we can apply AI to modernize the grid? First of all, as I mentioned, you need to have a solid understanding of the gaps or the challenges. And then once we know the challenges, we'll begin to see the opportunities. The opportunity for using AI is for grid planning. And how do we plan the grid? We need to have data uh, to be able to forecast any risk or to be able to avert any consequences that will happen. We have our grid now. The first reason why grid are modernizing is energy transition. So if imagine India decides to build a 500 gigawatt of renewables, but this renewable energy is so variable. It depends on weather, and then the weather begins to change, right? Once the weather begins to change, it means that we will have either more or less of generation. But there's always going to be demand. People will always demand electricity, right? So we need the opportunity to use AI here is to be able to study weather and then to be able to forecast ahead of time. And then once we're able to forecast ahead of time, it helps us in dispatching. So dispatch here is that there are several power plants in the country. You have a control center that decides how much each of these generation stations should produce. So if there's going to be a bad weather, let's say a snow within the next 2 weeks, it means that solar plants might not be able to produce more or will not be able to produce at all. And so the ability to forecast ahead of time by looking at historical weather data in a particular area helps us to tell the control center that okay, our plant will not be able to dispatch, let's say 200 megawatts for the next 2 weeks. And then the central control center is able to plan and call, let's say, a nuclear power plant that will be able to produce to balance the demand or the deficit. Okay, we will also be able to predict a load growth. Load growth is always going to be perpetual. Population is increasing. We are building more factories, and so in every country, as we have seen, like in India, there's always going to be like 9% growth. In USA, there's like 2% growth. Based on this knowledge, we'll be able to predict like, okay, in the next 10 years, we need to build this amount of power generations to be able to meet the demand. That is uh, load growth by using AI. And one thing you have to remember, I did not add it in this slide, is that AI did not start today. If you look at the history of AI, it started like in 1950s in energy systems, and then in 1970s, people started to implement it more. So this is not something new, but it is now more on a higher scale. We will be able to use AI for substation upgrades. Um, as I mentioned earlier on, most of the substation or the power grid assets were built several years ago. And so if you are building a new power plant that will interconnect to a substation, does the substation has capability to absorb or take in the new generation? Of course, maybe not. But how can we know this substation can take it? So by using historical data and then of the substation, getting information from all the the circuit breakers, the transformers, and then having a lot of data on them, how they are performing. Is this transformer overloading? You can look at 10 years ago, how if you have, let's say, a 100 MVA transformer, 10 years ago up to now, how was the transformer loaded? And the transformer, you could see like maybe 10 years ago, it was loaded 50%. And then the next 9 years ago, it was loaded like maybe 51%. But let's say 5 years ago, the transformer loading increased. And so the loading increased to, let's say, 80%. And then now the transformer is loaded 85%, 90%. And you don't want to overload the transformer. So having historical data of the transformer loading will be able to tell whether we need to upgrade the substation or not. Okay, we still have more slides, so I'll go a bit faster in order to be able to meet up our time. Site permitting, siting and permitting is also one of the things that we can actually use uh, AI to do this work. How can we do this? If you have ever designed a plant, you know there's a lot of permitting. You need to go through a land acquisition. You cannot just build a transmission line along the road. Every transmission, every power station you have ever seen is is based on a long-term designing procedures. So if you see a power plant building today, it did not start like 1 month or 2 months ago. Most of them started like 5 years ago. Some of the power plants, even designing stage, start like 10 years ago because you go through a lot of permitting, acquiring land rights. If the land is for government or it's for private owners, you need to go and talk to them. We need your land. You need to talk to the district or the municipal or the county. You need to talk to the state authorities. And then every state is different. For instance, in the US here, it's very, very complex. The same country, but every state has their own laws, their own rules. Not all engineering, you have like the baseline engineering, but states also have their own rules and regulations. So based on this, you would have a lot of documents to go through. But we all know if you want to use AI, you can use AI to summarize or to identify key things to look out for in huge permitting documents. So instead of spending like 6 months reading huge permitting documents, you can actually use AI to be able to summarize or look out for keywords or important things in document. So this is to be able to fast track or speed up your work, right? There are a lot of permitting code. You'll be able to use AI to be able to read all of these files and summarize them in 1 page or 2 pages. And who cannot read 2 pages? All of us can read 2 pages within a short time. So AI actually helps using AI tools in summarizing long text or long permitting document will reduce the time. Instead of spending a lot of time, we reduce the time. Okay. And then also, based on that, as I mentioned, we'll be able to identify some of the important things in this document, and then we can actually speed up the work. The next one um, is operation and maintenance and reliability. How can we do this? We can use AI to improve short-term load forecasting. We already looked at that. And then also optimize grid generation dispatch. So generation dispatch is knowing the amount of power you will be able to deliver to the grid at a particular time. It can be day or week or month. Okay, if you run a fuel power generation station, you know that you need a particular amount of fuel to be able to produce continuous electricity for the entire week or the entire month. If you don't have fuel, you will not be able to run. It's just like the way we use our vehicle. If you don't have fuel in your vehicle cannot run. But if you have enough, you'll be able to tell. You'll be able to tell like, okay, this fuel will last maybe 200 miles. And so maybe you drive a lot in 1 week, 200 miles is gone. And so your fuel is finished. So I will be able to predict asset degradation or failure in terms of operation and maintenance, right? We would be able, so operation and maintenance is a bit different from the last point we looked at here in grid planning. So there's planning and then there's operation, right? There's a planning stage where you need to actually know, okay, in planning, you would also plan about how much you can dispatch. But also in operation and maintenance, you also be able to you also be able to optimize your generation dispatch. Okay. And you would also be able to analyze reports, recognize human error, and provide any training if there is lack of expertise in the work. This one, if you ever work in any operating facility, Most of the times, I have worked in a control station before for several years. We normally take records when there's a fault. We take a log. We have a log book, right? We have a log book, and then we write everything inside. This is so archaic, like old, right? But also, we you have alarms that are captured on a SCADA. You have actions that are being taken from SCADA and the rest, and you would be able to have a history of actions, history of alarms and trips. Based on that, you have data, and then you can now study this data and know, okay, is it a human error? If it's human error, you'll be able to plan for training. That means that the people on the site may lack expertise and they need help. In terms of resiliency, we if we talk about resiliency, it's like whenever there is a problem in the grid, will the grid easily trip and then outage a lot of people, or will it be able to take in the shock and stay for some time? So we can use AI to identify and localize grid faults. We'll be able to restore service in real time. We will be able to synthesize extreme weather and create operator awareness. And also, we'll be able to coordinate distributed energy resources during grid disturbances and then support backup. So, distributed energy resources, you could have a lot of generation spread across. And if all of these are well coordinated, we can, if let's say we are losing one power source, one power generation source, we'll be able to take a fast action of bringing another power generation to balance the deficits. So AI has a lot of benefit in how we can apply the knowledge of how the grid is operating, how we get a lot of data, and then the actions to take. Okay, next, we have talked about a lot of fancy things that AI can do for great improvement, but this is not without the dangers that it also comes with. There's a lot of danger, especially in terms of the power systems. In terms of power system, the adoption of AI is not very fast, and there's a reason to that, because as of now, we have not fully understood all the AI models. We don't understand everything. And so there's a bit of caution. And then electricity sector is something that operators and reliability regulators do not want to play with. And so once you, because we don't, it's not something that you can do a simple test on, because losing electricity can cause um, a huge damage to every economy. So because of that, there's a bit of slow adoption. Most industry may adopt AI very fast as compared to the power industry. So let's look at some of the risks. Cybersecurity vulnerability, right? Attackers could manipulate demand forecast. So, and then they could also manipulate dispatch schedules and then fault detection. This is very critical, because if we talk about data and then we make this data more accessible to to any AI model, and then somebody is able to hack into this, they could change some of these things. So instead of giving the appropriate forecast, it's going to give you like something different. And then when this thing happen, right? When this thing happen, they could be false alarms, and then operators could just take a decision. So if we have a false alarm, an operator can say, okay, let me shut down this plant, and then shutting down the plant, what is the consequence? Okay, there's also a data privacy and then quality concern. Everything about AI relies so much on data and history. So, but where do we get this data from? Is this data quality? Is it coming from a reliable source, or is it already corrupted? So, if I'm going to train my model, right? on a data that is already corrupted, it's like garbage in, you have garbage out. So data privacy is a very huge thing in power systems, and it's not easy for a power operating facility to share their data to anyone outside the organization. It is if you cannot easily share the real data with a different company. So this is going to be one of the risks or one of the challenges also that comes with AI adoption in the in power systems. Uh, if you look at most tech companies, they can they can operate using a lot of data from external sources. But in terms of power, what I have seen in my experience is that you cannot easily share a private data. You cannot easily share that. So, and then even sharing that, and then people manipulating, corrupting that data will have a huge consequence, and you don't want to be in that situation. Okay, there's also the risk of we have interoperability and legacy system. So old system, if you have an old system and then you have a new system, how will you integrate? How will they interoperate? Right? Do you have to change all the old system in order to meet uh, the latest model, the latest standard? So that will require like a massive upgrade, and this is a huge risk, financial risk to companies who do not want to bear the financial risk of upgrading everything and then maybe not having any returns. And then there's also ethical issues and regulations, right? Ethical issues. Uh, Using a data from a particular company, is it accepted or is it not accepted? That is also another thing. So you can be an AI company and then you want to run a model using a data. Where do you get the data from? If you steal data from a particular company, that is going to be an ethical issue. Also, there's economic and workforce issues. The rising use of AI means that be there will come a time when most people traditional way of doing things will no more be there. And so what it means is that this is going to have huge impact on both investment as well as workforce displacement. So a lot of people could lose their job, right? If an AI can do something that a great operator does, it means that companies could come up and build AI agents, and these agents will displace people. So that is a risk as well. But the most important thing is we want to give job and opportunity to people. But um, companies care about the profits they will make. So if a company decides to use more of AI stuff, it means that we will lose people, we will lose the workforce, right? Okay, but we have talked about risks. Let's look at some opportunities here. There are opportunities as well. Whenever there is a challenge, there's an opportunity. But let's focus on some of the opportunities that we can get, right? Every country is different, but in the US here, there's a huge investment into AI, and as well as even in India too, there's investment and then even test prototypes that are being used in India in terms of AI. The opportunity is that you need to pivot whatever you are doing and incline more towards knowing what AI will do in the next 5 to 10 years. You need that knowledge. That is an opportunity for us. So in the US, you have the National Renewable Energy Laboratory exploring how AI can help with real-time decision support, how to predict controls, and then also scenario where we run 100% renewable energy or clean electricity, right? And then also resilience under cyber or extreme weather conditions. And then also prepared for situational awareness, better forecasting, anticipation disruptions, and optimizing responses. These are all opportunities for us, if you will leverage and then know how to use AI to do some of these things, you still stand the opportunity of getting job in those areas. Okay, I think I'll move straight to India. I have seen this Tata and Blue Wave using a pilot project where real-time data is being measured, and then the outcome of that experiment was that the AI was able to perform better than the legacy tools. Okay, and then after that, a 3-year deal was signed between Tata Power and then Blue Wave. So these are opportunities that we need to recognize that okay, AI is coming to stay. When computers came, people did not like to use computers, or even when internet came, most people did not want to use internet. But you need to think about it like AI is coming, it is here, it's coming to stay, and then the use of AI will permeate in all industries, including the power industry. The first question is how do you leverage, and then how do you leverage on this opportunity to upskill your skills, to learn new skills, such that when the opportunity comes, you will not be left out. Okay, so in conclusion, India, like many other countries, has made similar history and background about how the grid started and evolved till today. Right, there are critical lessons that we have learned throughout all of this. The evolution of the starting of uh, the starting of power grid has changed a lot of life, has led to industrialization, has led to improvement in healthcare, in food processing, manufacturing, and then most of all has also increased um, job opportunities for people. And this has brought about unprecedented human transformation. Now, the future of AI is for us to adopt the new skills that will be used in this industry. Even though it is not going to be so easy, it's not going to change overnight, but we need to adopt and know some of the important things that will help this industry. Okay, so in conclusion, the future of the grid won't end with us, but continue with perpetual needs for growth and prosperity, speed and dependability, reliability, stability, and resilience, and above all, human well being and safety. So I'll end my presentation here. It's over 1 hour. Thank you all, and stay connected with me through LinkedIn and through my website and my YouTube channel. Thank you so much.